Very well. Welcome everybody back to the meeting. This is section T12, Evolution 2. The first paper of this session is titled The Thermodynamics of Autonomous Human-Machine Teams, Control or Governance, and the presenter is William Lawless from Penn College, Georgia.
Thank you very much. Can you hear me okay?
Yes.
All right. I had my slides up in the other session, but I was in the wrong session. So I now have them coming up. Can you see them okay?
Yeah, that's perfect.
Yes.
Okay. So I've got 20 minutes and I've got about 30 minutes of slides, so I'll rush through them as fast as I can. My research is on the autonomous human-machine teams and whether they have to be controlled or governed. And it's a fundamental question. Looks like I don't have full functionality with my slides, but I'll push through them slide by slide. On slide 2, here's what our research team has done. As of June the 1st, we published our 5th book. This is on the artificial intelligence and human-machine shared context. And we've got a new contract with Springer. The last book was published by Elsevier. The next one will be by Springer. And I'm reviewing manuscripts now. If anybody's interested, please get in touch with me and I'll work with you on trying to get it published. But what I'd like to talk about today is a special issue of AI Magazine that we organized and got published in September and December of last year. In that special issue, one of the things that I talked about is Uber's self-driving car, which killed a pedestrian in 2018. The Uber car saw the pedestrian 6 seconds ahead of time, selected the brakes 1.3 seconds ahead of time, which was correct, but the brakes had been disconnected. The human operator saw the pedestrian 1 second before impact and apply the brakes 1 second after impact. So the Uber car worked as it was designed to work. However, the car did not alert its human operator when it could have. Therefore, it was a poor team player. In another article in AI Magazine last year, I made a bet that within 5 years, the machine will take over from an operator when the human operator is not responsive. And that's really what I want to talk about. There's broad change coming. Rapid decision-making is being advanced by machines, and autonomous human-machine teams will be put up against Skynet swarms. And there will be both military and civilian applications. Already in 2018, swarms have killed Russian soldiers at a Russian air base in Syria. Russia denied the deaths. The United States disavowed any involvement. But in 2018, and probably not for much longer, we've had as much as 30 minutes to react to ICBMs being launched by one nation against another nation. With hypersonic missiles, that reaction time is going to be reduced to virtually zero. So the question I'm posing is, can an autonomous human machine defeat a Skynet slave swarm? And that's going to pit governance versus the authoritarian control of swarms. Another question is, will humans give the authority to autonomous intelligent machines? Based on Uber self-driving car results, we may have no choice. Today, however, very little generalizes from the social science of individuals and human-human teams to human-machine teams. Here are two things that do generalize. In an interdependent state, a team's productivity can be greater than the sum of its members, which really impacts the rational model, which I'll get to in a little bit. And the second finding that does generalize is that a team produces two streams of entropy. One is from its team structure, which I've written about extensively, and another from its work products. And if a team minimizes its structural entropy production, that's kind of like focusing a telescope. It allows it to increase its maximum entropy production for work. With what we know, can we model interdependence for human-machine teams with Shannon information theory? And the answer to that is clearly yes and no. Shannon information theory is communication across a channel, which does not permit social information. Using Shannon, Conant predicted that teams will work best on a minimal communication. But minimum interdependence for teams, that's like zero Shannon information, which is the goal of swarms of slaves or the swarms of drones. Contradicting Shannon, however, we now know that the best science teams are highly interdependent. We know from Bisbee et al. That under highly interdependent situations, the teams are communicating via their structure. They're not talking. So what do we know about interdependence? Well, we know that interdependence builds shared context, and I've arbitrarily here broken interdependence down into three different effects: bistability, the measurement problem, and non-factorability. We're all familiar with the bistability. That's two-sided stories, multitasking, competition, deception. The measurement problem is something we don't talk about. We know about it, but we don't talk about it. And that is, if you've got two people or more people or two organizations in orthogonal roles, when you measure them, that interdependence collapses and leads to very poor correlations. We are all familiar with non-factorable information, where we have to use trade-offs to test uncertainty. Well, let's talk about bistability switching first. A deer in the forest, when it doesn't suspect the presence of a predator, will overgraze and harm the forest. But when it suspects that there's a predator about, it goes through bistability switching. So it'll take a bite of food, bite of grass, and scan for predators, bite of grass and scan. And that leads to healthy forest. We're all familiar with multitasking, where orthogonal roles produce information that does not sync up. And many of us are familiar with bistable illusions, which you see at the bottom left, where if you're looking at one interpretation, your brain cannot pick up the other interpretation simultaneously. Bistability implies duality, but in traditional social science of individuals, that's not the way they treat it. They treat action and observation as if they're one-to-one, which may be why it's very difficult to replicate social science experiments. Here's a really good example in the red box. These males had HIV, and the female mates of the HIV males participated in the study, where they would take a pill to prevent the transmission of HIV to them from their mates. At the end of the study, the women attested that they had been compliant 95% of the time, which meant that the drug had failed. At the same time, the researchers fortunately had collected blood samples, which indicated that their compliance was less than 26%. According to one of the researchers, she said that there was a profound discordance between what these women told us and what we measured. The problem, social states are interdependent, but they're bewildering to control, especially in the laboratory. The measurement problem is something that we're all familiar with too. It often leads to interpretation errors in the field. There are illusions like Adelson's AB illusion, which can tease it apart and show you its effect. And in the field, North Korea is a really good example of a country that does not allow bistability or two-sided stories to exist. And it can actually lead to de-evolution. So here's a nighttime photo of North Korea sandwiched between China and South Korea. I've had experience with minority control myself. I worked with the Department of Energy, and the Department of Energy's one-sided consensus seeking before 1983 grossly contaminated the environment. Look at this picture at the right. You see the Department of Energy covering up cardboard boxes of solid radioactive waste. Now, it had used cardboard boxes to dispose of 95% of its solid radioactive waste, which led to a great deal of contamination of the environment. After I got my PhD, the Department of Energy invited me to work with them. And at the bottom left, you can see that same burial ground. We got that burial ground closed in 2000. Here's the bottom line. When the Department of Energy had complete control of the decisions it made, it actually crapped up the environment, did a lot of damage. But today, the Department of Energy has oversight by many different groups: the National Academy of Sciences, Defense Nuclear Facilities Safety Board, the state of South Carolina, and citizens. And yet the Department of Energy is making pretty good decisions. Non-factorability. We're all familiar with endless fights, but deciding who is right is really a difficult thing to do. CBS and Viacom fought for 2 years over their merger. And in that 2-year period, they lost a lot of money. At the bottom left on this slide, you can see nighttime photos of Syria in 2012 and 2014. And you can see that the country by 2014 was being torn apart. And here's at the bottom right, a picture of a split corpus callosum. When the brain has been split into two halves, one of the most interesting things about that is that the two halves of the brain see reality differently. And that leads to non-factorable information. Non-factorable information supports the subadditivity of orthogonal roles. I talked about this morning. When weak teams are disturbed, they generate copious amounts of Shannon information. That's like CBS and Viacom. Interdisciplinary science teams, the worst performing science teams, and divorce teams. On the other hand, perturbations of the best teams generate very little information, which implies that subadditivity is going along. If interdependence is bewildering, what can we predict? Well, my hypothesis is that the more redundancy there is in a team, the worse the team will perform. Comparing that to social network analysts, they believe that as redundancy increases, the network becomes more efficient. The National Academy of Sciences had found that many hands make light work. So how does that compare with my predictions? The next slide, I've found results that contradicted both the social network theory and the National Academy of Sciences, and that was published in the Journal of Math Psychology on the left. And I repeated that study using Kullback-Leibler divergence and found that corruption actually increases the effect, and that was published in Frontiers in Physics. The third test I've done looks at team intelligence and whether or not that plays a part in increasing maximum entropy production. And the results, I looked at data from the United Nations for 19 Middle Eastern, North African nations and Israel, and I found a significant support. And that was published in Foundations of Science. But here's the key finding. My 2019 finding is that schooling, the amount of school that is involved, which is a surrogate for intelligence, is significantly related to the amount of patents that a country produces. However, that's incommensurable with the finding that I got in 2001, which is that training but not schooling is associated with the best fighter pilots. These two findings, I think, are really key going forward. One is tapping in intellectual thinking, and the other one is tapping, the bottom one is tapping a physical skill. So here's a comparison of rational models versus interdependence theory. The traditional model by Tetlock and Gardner is that forecasting is a skill that can be cultivated. But their first super forecast of Brexit and second that Trump would not become president both failed. The problem is that facing uncertainty or conflict, rational models fail, while interdependence theory thrives. Confronting uncertainty or conflict, humans exploit bistability with trade-offs in debates. And we see that with majority rules, which lead to the best legal decisions. Justifying competition, a debater uses trade-offs to seek the vulnerability in an opponent to reduce their maximum entropy productivity and increase their structural entropy production, which shows that they're actually making slower team responses. So that leads to the fourth model, a debate model to confront uncertainty with conflict. In this one, I looked at the Department of Energy in the United States versus the Nuclear Regulatory Commission, which got into a long-winded debate over 7 years to close high-level waste tanks, highly radioactive waste tanks, which is located or denoted on this image at the bottom right in 1 and 2 on an imaginary axis. Until the debate before the Citizens Advisory Board, which led to immediate action. So when this debate was brought before citizens, they forced the Department of Energy and the Nuclear Regulatory Commission to compromise and get those tanks closed.
2 more minutes.
Here. So applying the debate model, rational models work very well for individuals in predictable situations with certainty or well-defined problems. That's physical network theory and game theory. But they don't work well under conflict or where there's a lot of uncertainty. And that's when the debate model comes to the fore. And what that tells us about human-machine teams, and this is the bottom line of my talk, is that machines must be able to explain their positions, however imperfectly. And I can stop at that point. Here's my conclusion slide. How much time do I have?
1 minute. 1 minute.
Okay, I'd like to address thermodynamics here in the this second bullet highlighted in bold. As a last team member fits, here's a very interesting prediction. Entropy reduces and minimum redundancy under competitive interdependence leads to maximum entropy production. So poor teams waste entropy to disband. Good teams are not wasting their energy. And that's it. Are there any questions?
Thank you very much. Perhaps we have time for one short question if someone wants to ask. I wanted to ask a short question. When you say that bad teams generate information, do you mean that as noise?
Uh, Poor teams are, let's talk about divorce, which every human is familiar with. That divorce can be a business team, two businesses that are breaking up, or a husband and wife that can break up. They're generating copious amounts of information as they break apart. That information is pretty much noise. It's not really helpful information. You can't use that information to troubleshoot. On the other hand, when you got a really good team that's working together very well, they're generating very little noise. So it's hard to figure out why a good team is working well, and it's impossible with all the information a poor team generates to figure out why they're not working well.
Thank you very much. I think we can move on to the next presentation.